What we've been talking about over the last two lectures is how the quantum states that are allowed for electrons in solids are occupied. We derived the Fermi energy, for instance, in the context of the free electron gas, which assumed that the electrons in a conductor were free to move however they wanted, within the confines of the chunk of material. When we added a periodic array of delta function potentials to approximate a crystal, very periodic array of atoms, and allowed the electrons to interact with those atoms, we ended up with band structures for those energy levels. The energy levels came in bands. The occupation of those energy levels can be thought of simply as starting with the electrons in the lowest energy and then adding up, filling energy levels, pouring electrons into the lowest energy, as if we were filling a glass of water, starting with the bottom and going up to the top. It's not as simple as that, of course, and the way in which those energy levels are occupied is the subject of something called quantum statistical mechanics, which is a very deep topic that I'm only really going to be able to scratch the surface of, so this is really just an intro to quantum statistical mechanics. The fundamental concept of statistical mechanics is that we don't really care about how the system evolves with time. We only care about the configuration of the system. And the assumption is that every state with the same total energy is equally likely. Essentially, if you have a set of states that have the same total energy, for instance, we know the temperature of a material, we know the total amount of energy, then the time that the system spends in each of the states that satisfies that total energy constraint are going to be equal. So if we observe the system at any given time, we're equally likely to find it in each of the allowable states. This is ignoring a lot. We're assuming a structure for the probabilities, we're ignoring the details of the evolution of the system, and we're only really considering conservation laws. How many particles do we have that we need to assign to quantum states? How much total energy do we have that we need to account for? One way to think about this from a very simple sort of first principles context is to consider three particles in a box. I'm going to consider a very specific example now. Just three particles, but they're free to move within a box and they're not interacting with each other. So instead of the free electron gas where we had a large number of particles, we're just considering three. The energy of each particle in a box is going to be given by a quantum number, some n, lowercase n here, n sub a, n sub b, or n sub c for each of the three particles. And the energy is essentially the sum of the squares. There's some ground state energy, the 111 energy, or the energy associated with a three-dimensional particle or a one-dimensional particle in a box in the x direction. So these are just three one-dimensional particles now, and their energies sum up like this. I'm going to steal the example from Griffiths, and he gives the example of what if the total energy of the state is 363 times the energy of a single particle. You can make the number 363 in a lot of ways by combining n sub a squared, n sub b squared, and n sub c squared. And you can do it, for instance, by taking 11 squared plus 11 squared plus 11 squared, or 13 squared plus 13 squared plus 5 squared, or 5 squared plus 7 squared plus 17 squared, etc. These are the ways in which we can make the total energy 363. So if we have a quantum mechanical system composed of three one-dimensional particles in a box, we have a certain set of allowable combinations of quantum numbers. These are essentially our allowed quantum mechanical states. We have one state with 11, 11, 11, and you can see already probably where this is going. If I have distinguishable particles, 11, 11, 11 is an allowed state, whereas if I have fermions, 11, 11, 11 is not an allowed state because I've put multiple particles in the same quantum mechanical state. I won't be able to make an exchange antisymmetric wave function this way. For bosons, maybe it's not a problem. Well, what actually happens is if we're working with distinguishable particles, first of all of these states are equally likely. So I have one state with 11, 11, 11, three states with 13, 5, 13, 13, 5, three states with 1, 1, 19, six states with 5, 7, and 17, distinct by the order. If the particles are distinguishable, these states are all distinguishable. The 5, 7, and 16 is distinct from 7, 5, 17, for instance. So in distinguishable particles, there's no problem with any of these states. With our fundamental assumption in statistical mechanics that all states with the same energy are equally likely, I can calculate some probabilities. for instance, suppose I drew one of these particles at random, and I wanted to know the probability that the particle would have energy 1. Well, energy 1 occurs in this state, 1, 1, 19. So the probability that my quantum system will be in this state is 3 possible states out of 13 total. 3 divided by 13 times the probability that if the quantum mechanical system is in that state, 1, 1, 19, that I draw one of the 1s for my particle in question, which is, well, 2 of the 3 particles are in state 1. So here I will multiply by 2 out of 3. And that gives me my overall probability that I would draw a particle with state 1. If I want to know the probability that I would draw a particle with state 5, for instance, well, 5 occurs in a couple of ways. It occurs here and it occurs here. So what I would have is, for this case, or this case, I can have a particle with energy 5. In this case, the probability that the system overall is in a state 13, 13, 5, well, there's 3 possible states that way, 3 out of 13, times the probability that I get 5 if the system is in this state, 1 out of 3, plus the alternative, the probability that the particle is in this state, 6 out of 13, times the probability that the particle is in the state 5, given that the particle is in one of these states. Again, 1 out of 3. You can continue these calculations for all of the different allowable energies here, and you'll end up with a total number of probabilities that describe the likelihood that a particle will be drawn with a given energy. Essentially, these probabilities tell you the distribution of particle energies for a system described by 3 one-dimensional particles in a box in quantum mechanics with total energy of 363. This is if the particles are distinguishable, however. If the particles are bosons, bosons are not distinguishable. That means that whereas we had 3 states with 13, 13, 5, distinguished by the order of the particles, 5, 13, 13, 13, 5, 13, and 13, 13, 5, if the particles are bosons, they're indistinguishable, and we would have to make an exchange symmetric combination of those 3 distinct quantum states, and that would be the only allowed quantum state with the 13, 13, 5 combination. 2 bosons in state 13 and 1 boson in state 5. So essentially, for bosons, I would have just one state 11, 11, 11, just one state 13, 13, 5, just one state 1, 1, 19, and just one state 5, 7, 17. So I would have 4 total states, which means instead of dividing by 13 in my first number in my probabilities here, I'd be dividing by 4. So if I wanted to calculate P1, for instance, the probability 1 only appears in this state. There is one allowable state for bosons with the quantum numbers 1, 1, 19. So my P1 would be 1/4, because there's only one state that has 1s in it, times the probability that the particle, given the system is in that state, that the particle drawn would be in quantum state 1, which is, as before, 2 out of 3. If I wanted to calculate P5 for the bosons, 5 again appears in 2 separate places, but now there's only one quantum state with 13, 13, 5, so 1 out of 4 probability that the particle will be in that state, times 1 out of 3 chance that the particle that's drawn will be in the state 5, given that that the overall quantum system is in the 13, 13, 5 state. That's for this quantum state. There's also this quantum state. But again, there's only one quantum state here, so I would have 1/4 times, and again, 1/3. Because there's only one of the 4 quantum states here that I'm considering, and that particular quantum state has the probability 1/3 the particle will have energy 5. So you can make these calculations for bosons as well, and because of the symmetrization under exchange required for bosons, you would have a different set of probabilities. Now, if I wanted to repeat this calculation for fermions, the results are still, again, different. For fermions, 11, 11, 11 is not an allowable quantum state because there's no way to make an exchange antisymmetric version of this state. So this is not allowed. There's 0 quantum states, 11, 11, 11. Same for 13, 13, 5. When I exchange the two 13s, I'd have to get opposite the wave function, but I can't do that. There's no exchange antisymmetric combination here. I've put two particles in the same quantum mechanical state. Not allowed, according to the Pauli exclusion principle. So my second state and my third state are out. The only possibility that remains is my fourth state, and as before, indistinguishable particles means there's only going to be one possible state for this system. So 3 of my 4 possibilities are out, and my probabilities then are relatively easy to write down. If I want P1, well, P1, there's only one quantum mechanical state that had a particle in the one state, and that was not allowed for fermions. So P1 is 0. P5, on the other hand, P5 is still allowed. There is a 5 here. And it's just going to, the probability of 5 is the probability that the particle is in this quantum, or the system is in this quantum mechanical state, which is 1 out of 1, the only allowable quantum mechanical state. And the probability that the particle that's drawn from that quantum mechanical state has energy 5 is just going to be 1/3. So the energy distributions you get and the allowable states and the overall probabilities you calculate depend on whether the particles are distinguishable, bosons, or fermions. This basic example is, of course, unusually specific because, well, I've given you a specific system to consider, 3 particles in one-dimensional particle in a box of states, and that the total energy is 363. Specifying the total energy is analogous to specifying the temperature, as we'll see shortly. But ideally, we would be able to do something much more general than simply consider particles like this and enumerate states and calculate probabilities by hand. This is very cumbersome. But it is actually the basis of the quantum statistical mechanics. So we would like to answer these probability questions with more generality. Instead of working with a specific state, is it possible to come up with expressions for how these probabilities work out for a more general quantum mechanical system? Well, the probabilities can, in fact, be worked out in general. What we're interested in now is the configuration of the quantum mechanical system, and there are a couple of ways to look at that. First of all, you can consider n1, n2, etc., up to infinity, potentially, the number of particles that exist in each of the quantum mechanical states, state 1, state 2, state 3, etc., analogous to the subscript 1, the subscript 2, the subscript 3, etc. when I was calculating particles, or probabilities in the previous slide. So this tells us essentially the number of particles in each quantum mechanical state. Another essential ingredient here is the number of quantum mechanical states that exist at each energy. And that's related to the degeneracy, which I'm going to call D. So if we know the degeneracies of all the quantum mechanical states, that's another essential ingredient to our calculation. What our goal is, in calculating these things, is something that Griffiths calls capital Q. Q tells you the total number of distinct quantum mechanical states that exist at a particular, for a particular configuration. So Q depends on the configuration. It depends on the number of particles in state 1, the number of particles in state 2, etc. It's essentially an infinite dimensional function. And if we can understand this infinite dimensional function, well, a function of infinitely many variables, we'll be able to understand essentially how the probabilities work out. Subject to the fundamental assumptions of quantum statistical mechanics that all of the states that satisfy a given energy are equally likely, knowing the number of distinct states that have a particular configuration essentially tells us the probability of that quantum mechanical configuration. Since we're dealing with indistinguishable particles, for the most part in quantum mechanics, all we really need to know are the n1, n2, etc., and the degeneracies, and we'll have expressions. Now the mathematics that happens here is quite complicated in principle, but what you end up working with is essentially a lot of counting arguments. How many ways are there to choose n particles from a pool of n plus 1, for instance? If you answer enough questions like that, and you work through the algebra, and Griffith spends about 10 pages doing all of this, you end up with results like the following. For distinguishable particles, Q is equal to n factorial, where n is the total number of particles, times a product. And the product, I'm going to take over variable I equals 1 to all the way to infinity of the degeneracy of the state I raised to the power given by n sub I, the number of particles in that particular quantum state, divided by n sub I factorial. That's the number of distinct quantum states, if the particles are distinguishable, distinct configurations, distinct assignments, if you will, of particles to the quantum mechanical states described by these degeneracies. We'll also need to know the energies associated with these quantum mechanical states, but that enters later. So for distinguishable particles, you can actually see the effect of the distinguishability of the particles very clearly here, this n factorial term. N factorial is the number of distinct orders that you have for n items. So if I have n particles, there are n factorial different orders. N factorial, of course, is a very, very large number, so these sorts of expressions aren't the types of things that you would actually want to calculate with, but you'll see how they're used in a moment. You can make similar arguments for bosons and fermions, and what you get, for instance, for bosons, is that Q is going to be, where to go? Q is a function, simply a product now, from I equals 1 to infinity, of n sub I plus d sub I minus 1 factorial divided by n sub I factorial d sub I plus 1, minus 1 factorial. That is your expression for bosons. And for fermions, your expression looks similar to the expression you get for bosons, only slightly more simple. It's again a product from I goes from 1 to infinity of simply the degeneracy of the ith state factorial divided by the number of particles you're assigning to state I factorial times the degeneracy of the state I minus n sub I factorial. So these are our expressions for the total number of states. And there's, like I said, about 10 pages of algebra here, arguing about what the proper way of assigning particles into states are, and if there's a clever way of counting the number of different ways that those states can be assigned, etc. There are some very clever arguments here. It's a very beautiful topic, but I'm not going to require you to delve into the mathematical details here. So given these things, how do we actually use these Q values? The Q values tell you the number of distinct ways in which a particle can obey these sorts of things, or a quantum system can have these sorts of numbers assigned to it. So n1, n2, n3 tell you the number of particles in state 1, state 2, state 3, etc. And there have to, of course, be, for the case of fermions, a higher degeneracy than the number of particles that you're working with. We're still subject to those exchange anti-symmetry / Pauli exclusion principle constraints. But given these Qs, what sort of things can we calculate? Well, the Qs essentially give you the probabilities, and it is a strange fact of statistical mechanics that for large numbers of particles, the system becomes very, very, very likely to be found in the most probable state. Essentially, what we're going to assume is that the system is essentially always in the state that maximizes Q. That's a very strange thing. What we're looking for is the most probable configuration, and we're going to find that by maximizing Q. Maximizing Q is essentially a multivariable calculus problem, and it's a doozy, so I'm not going to make you delve into the details. But if you maximize Q, essentially what this is saying is that the fact that the system is very likely to be in the most probable state, or very near it, is a statement along the lines of, if I flip a coin 10 times, I might only get 3 heads, and that's unlikely. But if I flip a coin 10 million times, it's very, very, very unlikely that I would get only 3 million heads. So 3 out of 10 versus 3 million out of 10 million are very different from the probabilistic perspective. And if I have a lot of particles, if I flip a lot of coins, I'm likely to get something very close to the most probable configuration, the 50-50 split in the case of coin flips, or the configuration that maximizes Q in the context of quantum statistical mechanics. So we want to maximize Q, and what's more, we want to maximize Q over the space n1, n2, etc., up to n sub infinity. This is an infinite dimensional space. What's more, we have to maximize Q subject to constraints. And the constraints we have are that the total number of particles is, for instance, known. So if I sum over I, n sub I have to get the total number of particles. Every particle in the quantum mechanical system has to be somewhere, has to be in one of the states. We also have to maximize Q subject to an energy constraint, namely that if I sum over I of the energy of the ith state times the number of particles in the ith state, I have to get the total energy in the system. This is an expression of conservation of energy. This is an expression of conservation of particles. If I can make that maximization, I will have my answer. And it is actually possible to maximize those functions. You have to use a method of maximization, or constrained optimization in this case, called Lagrange multipliers. Essentially what we do is replace Q with a function g, where g is defined as, well, it's a function of the same things that Q is a function of, but it has some additional stuff added on. One simplification you can make is that instead of maximizing Q, to maximize the natural log of Q. The reason you do that is because natural logs of a product is the sum of the natural logs, and it's much easier to work with sums than products. So first of all, when we define g, we're going to maximize the natural log of q. Constraints are added in the context of Lagrange multipliers by simply adding on some term with some constant multiplying it that accounts for the constraint. So in this case, my constraint is going to be n minus sigma sum over I of n sub I, and I'm going to have another term added on for the constraints on total energy minus sum over I, n sub I, e sub I. Now if you think about what it means to maximize this, I've added two additional variables. Instead of just having n1, n2, etc. up to n infinity, instead of infinitely many variables, I have infinite variables plus alpha and beta. I have two additional variables. If I take the derivative of g with respect to alpha, I'm just going to end up with this expression, which is my constraint. If I take the derivative with respect to beta of this overall expression, I'll just end up with this expression, just my constraint. So if I simultaneously optimize the function g over n1, n2, etc., and alpha and beta, by taking derivatives of g and setting them all simultaneously equal to 0, I will automatically account for both maximizing the natural log of q and account for my constraints. Now, there's a lot of mathematics going on here, and I'm not expecting you guys to follow entirely, but from pages 237 to 241 in the textbook, Griffiths goes through this optimization to find the system that has the configuration of the system that has the maximum probability, the most probable configuration. What you do when you find the most probable configuration is that alpha is related to something called the chemical potential, mu. Mu is related to the Fermi energy. Essentially, mu is the potential energy per atom, or incrementally, the amount of energy you'd have to add to the system to add one more particle. That's sort of a definition of chemical potential. You may have studied it in your chemistry class. Beta, on the other hand, is related to the temperature. KBT in this case, because we're working with temperatures in the context of energies, we have to invoke Boltzmann's constant, which is something you get from classical physics. What you get then, going through all of this procedure, is that for distinguishable particles, you get essentially that the number of particles that are going to be assigned to a particular quantum mechanical state in the most probable configuration, and I'll write that as lowercase n, which is going to be a function of the energy of the state, is given by, in the case of distinguishable particles, e to the minus energy minus mu over kb t, where this epsilon term is representing the energy and mu is representing the chemical potential. That's if the particles are distinguishable. If the particles are fermions, you end up with something that looks quite different. The number of particles in each quantum state as a function of the energy of the state is equal to 1 over e to the epsilon minus mu over kb t plus 1. And for the case of bosons, you get n of epsilon is equal to 1 over e to the epsilon minus mu over kbt minus 1. So the only difference between fermions and bosons is this plus sign or minus sign in the denominator of an expression which looks sort of similar to the distinguishable particles case, but not really. If this plus or minus 1 weren't here, you would get something that was quite similar, essentially identical, 1 over e to the something is, of course, e to the minus that same something. But these distributions behave themselves very differently. In terms of naming, this is called the Fermi-Dirac distribution, and this is called the Bose-Einstein distribution. For all of Einstein's talk that he didn't really like quantum mechanics and he felt like it was an incomplete theory, he did make some remarkable contributions. This is one of them. So these distributions, these are really the important results of quantum statistical mechanics. The Fermi-Dirac distribution and the Bose-Einstein distribution in particular are very important. They tell you the number of particles that will occupy a particular quantum mechanical state at energy epsilon as a function of the energy. That, for instance, is what you need to know. If you draw a particle at random from a quantum mechanical system and you want to know what the likelihood is that it will have a particular energy, that likelihood is essentially given by these distributions. We now have the machinery we need to answer that fundamental question, one of the questions we started off with at the very beginning: how to explain the blackbody spectrum. The blackbody spectrum, if you recall, is a function, let's call it rho of omega, as a function of omega, and it looks something like this. Early on, people had noticed that there was a well-defined form for this density, the intensity of light emitted by a material at a particular temperature, as a function of the frequency, or alternatively as a function of the wavelength. And you could figure out what the asymptotic behavior was on both ends of this spectrum, either by making some numerological observations or by making some classical physics arguments. But you could not justify the unison of those numerological arguments with the classical physics arguments until quantum mechanics came along. You can explain the blackbody spectrum simply as the Fermi-Dirac distribution, essentially. It's not the Fermi-Dirac distribution, it's the Bose-Einstein distribution, subject to some modifications to account for the fact that we're talking about photons and not electrons. The fact that we're not fermions, or bosons specifically. Photons behave a little bit differently. First of all, we need to know the energy associated with the quantum mechanical state, and in the case of photons, that energy is given by h nu, or alternatively by h bar omega. If you know the frequency, you know the energy of the photon. We also need to know something about the k vector, the momentum space behavior of the wave function, and that's given by 2 pi divided by the wavelength of the photon. And in the context of photons, you know that the wavelength and the frequency and the speed are all related. So the k, in the case of the photon, is omega over c. Photons are bosons. They have integer spin, but they behave a little differently than the bosons we're used to, since essentially they're massless. That implies some additional constraints, which you'll learn about in relativistic quantum mechanics. But what is necessary for the purposes of understanding the blackbody spectrum is that there are only 2 spin states. The photon naturally has spin quantum number 1, so you would expect that it would have +1, 0, and -1 allowable components of the z component of the angular momentum. But in the context of the photon, +1 and -1 are the only allowable quantum states. Essentially, it's not possible to have a photon with z component of angular momentum 0. The final modification is that the number of photons is unconstrained. The number of photons can change with time. What that means is that in our optimization we would set alpha equal to 0. That removes it effectively from our constraint, or alternatively that the chemical potential mu is 0 in our final result. One last mathematical difficulty is that if we're looking at this in terms of omega, well, we have to work with d omega in our integrals instead of dk. If you go through all of this, converting from dk to d omega, using expressions for the energy, allowing for 2 spin states, and setting alpha and mu equal to 0, what you end up with is the formula for the blackbody radiation spectral intensity. H bar omega cubed divided by pi squared c cubed e to the h bar omega over kBt minus 1. And this formula can be used to predict many things. In particular, it can predict the energy density, energy per volume, is proportional to temperature to the fourth power. Or it can predict that the wavelength of maximum intensity is proportional to 1 over the temperature. This is Wien's law, if I recall correctly. So, quantum statistical mechanics is essentially the answer to the question, whence the blackbody radiation spectrum? It's a mathematically very rich subject. It's very interesting, but the level of complexity here, since we're getting down to the end of the term and you're all starting to get really tired of this stuff, is a little bit above and beyond what I would expect you to reasonably do. What I do need you to do, though, is to understand how the Fermi-Dirac and Bose-Einstein distributions actually behave. So, to check your understanding of the Fermi-Dirac and Bose-Einstein distributions, describe the shape of the distribution for the temperature equals 0 case, for both of these distributions. And then finally, just so that you're understanding a little bit of the derivation here, explain in your own words why I threw out the 11-11-11 state in my calculation of probabilities for fermions. If you've got those basic facts down, you have a basic understanding of how to use the results of quantum statistical mechanics, you're in good shape. Of allowable combinations of quantum numbers. These are essentially our allowed quantum mechanical states. We have one state with 11, 11, 11, and you can see already probably where this is going. If I have distinguishable particles, 11, 11, 11 is an allowed state, whereas if I have fermions, 11, 11, 11 is not an allowed state because I've put multiple particles in the same quantum mechanical state. I won't be able to make an exchange antisymmetric wave function this way. For bosons, maybe it's not a problem. Well, what actually happens is if we're working with distinguishable particles, first of all of these states are equally likely. So I have one state with 11, 11, 11, 3 states with 13, 5, 13, 13, 5, 3 states with 1, 1, 19, 6 states with 5, 7, and 17, distinct by the order. This is ignoring a lot. We're assuming a structure for the probabilities, we're ignoring the details of the evolution of the system, and we're only really considering conservation laws. How many particles do we have that we need to assign to quantum states? How much total energy do we have that we need to account for? One way to think about this from a very simple sort of first principles context is to consider 3 particles in a box. I'm going to consider a very specific example now. Just 3 particles, but they're free to move within a box and they're not interacting with each other. So instead of the free electron gas where we had a large number of particles, we're just considering 3. The energy of each particle in a box is going to be given by a quantum number, some n, lowercase n here, n sub a, n sub b, or n sub c for each of the 3 particles. And the energy is essentially the sum of the squares. There's some ground state energy, the 1, 1. What we've been talking about over the last 2 lectures is how the quantum states that are allowed for electrons in solids are occupied. We derived the Fermi energy, for instance, in the context of the free electron gas, which assumed that the electrons in a conductor were free to move however they wanted, within the confines of the chunk of material. When we added a periodic array of delta function potentials to approximate a crystal, very periodic array of atoms, and allowed the electrons to interact with those atoms, we ended up with band structures for those energy levels. The energy levels came in bands. The occupation of those energy levels can be thought of simply as starting with the electrons in the lowest energy and then adding up, filling energy levels, pouring electrons into the lowest energy, as if we were filling a glass of water, starting with the bottom and going up to the top. It's not as simple as that, of course, and one energy, or the energy associated with a 3-dimensional particle or a 1-dimensional particle in a box in the x direction. So these are just 3 1-dimensional particles now, and their energies sum up like this. I'm going to steal the example from Griffiths, and he gives the example of what if the total energy of the state is 363 times the energy of a single particle. You can make the number 363 in a lot of ways by combining n sub a squared, n sub b squared, and n sub c squared. And you can do it, for instance, by taking 11 squared plus 11 squared plus 11 squared, or 13 squared plus 13 squared plus 5 squared, or 5 squared plus 7 squared plus 17 squared, etc. These are the ways in which we can make the total energy 363. So if we have a quantum mechanical system composed of 3 1-dimensional particles in a box, we have a certain set, the way in which those energy levels are occupied is the subject of something called quantum statistical mechanics, which is a very deep topic that I'm only really going to be able to scratch the surface of, so this is really just an intro to quantum statistical mechanics. The fundamental concept of statistical mechanics is that we don't really care about how the system evolves with time. We only care about the configuration of the system. And the assumption is that every state with the same total energy is equally likely. Essentially, if you have a set of states that have the same total energy, for instance, we know the temperature of a material, we know the total amount of energy, then the time that the system spends in each of the states that satisfies that total energy constraint are going to be equal. So if we observe the system at any given time, we're equally likely to find it in each of the allowable states.